Our next topic is actually chemistry of carbocations. So we have studied what is called a carbocation. If carbon is having a positive charge, it is called actually a carbocation. We have seen the structure of carbocation before, but again we will be discussing the structure in the due course. You can see that it is actually a methyl carbocation. This is a primary carbocation. It is actually a secondary carbocation. It's a tertiary carbocation. If we look into the number of hyperconjugated structures, you can see that this methyl carbocation is having no hyperconjugated structures, while this primary carbocation is having 3 hyperconjugated structures because it is having 3 alpha hydrogen atoms. It will be 3 alpha hydrogen atoms. Okay, so you can see that here in this case, there are secondary, there will be 6 alpha hydrogen atoms. Okay, and in this tertiary, we will be having 9 alpha hydrogen atoms. And you can see that more the number of hyperconjugated structures, more will be the stability of carbocation. Therefore, tertiary carbocation are more stable because of hyperconjugation. If we look into the carbocations, aliphatic carbocations and aromatic carbocations, it is actually benzylic cation. Benzylic cation. So we can say in benzylic cation, there is a possibility of resonance. Okay, the possibility of resonance, you can see that it's a positive charge system. The electron in the aromatic ring goes towards this exocyclic system and it can form a system like this, and it can undergo further electron delocalization, and these 3 structures are possible, and it finally comes back to the original configuration. Okay, so benzylic cation is also stable. It's actually due to resonance. So when you compare aliphatic and aromatic carbocations, always aromatic carbocations like benzylic carbocation is more stable because hyperconjugation is there in aliphatic carbocations, but in aromatic carbocations there is resonance, and resonance is more stronger than hyperconjugation. You can see this is actually a system called allylic system. It's actually allylic system. So this is an allylic cation. It's called an allylic cation. So we can see that allylic cations can also undergo resonance. So allylic carbocation is also stable carbocation. Again, this is an allylic carbocation. It's allylic. Okay, allylic cation is actually an aliphatic straight chain carbocation. When you compare to, this is more stable carbocation because it's an allylic system. Allylic system is stabilized by resonance on some of the effect. Now again, this is again an allylic system. This is double bond, then CH2 plus the allylic system. You can see here there's conjugation possible, and therefore you can see that we get a resonance structure like this. Okay, so it will be more stable when you compare to that of this non-allylic system. This benzylic system is more stable than cyclohexyl system because there is no resonance here. And if you see here, it is a double bond. It's an allylic system. It's another allylic system. And there are 2 allylic systems here, but here we have got only 1 allylic system. So you can see that the system is additive. It's additive because this is 1 allylic contribution, is second allylic contribution. They are actually additive, and that will increase the stability. Here we have only 1 allylic system. Here we have got 2 allylic system. System with 2 allylic systems are more stable. The normal carbocations are not stabilized by resonance, in fact. These are the comments about stability of carbocations. And you can see that for important reading, you may refer to this book, Ian Fleming, Molecular Orbitals and Organic Chemical Reactions. It's actually a very pioneering book on molecular orbital theory. As I discussed in the regular class, you know that these days molecular orbital concept is actually under a lot of debate. But still, this book is considered to be one of the very good book for understanding the orbital interactions, in fact. Now let us look into the structure of carbocations. This is the top view of carbocation. There will be 3 hybrid orbitals, sp2 hybrid orbitals, and there is plus charge in the central carbon atom. This is the top view, and you can see this is the side view of carbocation. You can see that here there will be one carbon atom and this hydrogen there on the same plane. This H is towards you, towards me. Okay, and this is actually beneath this surface, is below the surface. Or you can say it's actually in the out of the plane. And there's a vacant p orbital. It is actually perpendicular to the molecular plane or the carbocationic plane. This is a top view and the side view. The shape of the molecule is what it's trigonal planar. Shape is trigonal planar. And the typical angle is 120 degrees. Okay, this is another way to predict the shape of the carbocation. We can see that there's an empty orbital. Empty orbital, it's in the molecular plane. You have seen SN2 reactions. SN2 and SN1 reactions. In SN1 reactions, there will carbocation is formed as intermediate. And you can see SN1 reactions, there is actually carbocation, and this carbocation is having lobes above the plane and below the plane, and the nucleophile can attack from this plane, and the nucleophile can attack also from this plane. So this will give rise to the racemase product. Okay, so we can use this orbital picture to explain the stereochemical outcome of the SN1 reactions. Now it's the time to study the preparation of methods of preparation of carbocations. Now we're going to see the methods of preparation of carbocations. Typically, carbocations can be made from alkenes. For example, it's it is styrene. Styrene, it takes it reacts with HBr. First what happens is that the double bond adds gives to the H, and Br will become Br minus, and the carbocation is formed. It forms a benzylic carbocation. It's actually a benzylic carbocation is formed. So typically, we can say that we can make carbocations from alkenes. So one of the method of preparation of carbocation we can make from alkenes. It's actually a very typical method of preparation of carbocations. Similarly, if you have got this compound, it's another alkene. In presence of an acid H plus, acid H plus is there, electron get donated to H plus, and here there will be H, and there is the plus charge over here. It forms the special carbocation here. Another way is from the ketones. The ketone in presence of H plus. It can form, you can see that there are two lone pairs in oxygen atom here. It gets donated to this hydrogen atom, and it becomes like this O plus H. Oxygen is electronegative, but here you can see that oxygen is having positive charge, it is highly unstable. So what happens is that this will donate electron to itself. As a result of that, it forms plus here, and here will be OH. It's actually a carbocation. Again, a carbocation. Second method of preparation of carbocation is from alcohols. So it's a secondary alcohol. Alcohol on presence of acid, H plus. First it forms a protonated alcohol. You can see that there are two lone pairs in the oxygen atom. The lone pair is donated to H plus. It forms a protonated alcohol. Later, the protonated alcohol will undergo elimination of water, that means dehydration. Okay, so water goes up and the carbon develops positive charge. It forms an isopropyl carbocation. It's a secondary carbocation. Similarly, if there is ammonia, amines, sometimes in presence of acid, sometimes it also forms a protonated amine. It will eliminate ammonia molecule and it forms R plus. It's actually a second, it's also a method of preparation of carbocation. Now we are going to see the discussion. We are going to discuss the mechanism of the process in detail. So this is the reaction here. For example, we are going to consider another example, a very complex example. This is a compound. The compound is 3,3-dimethyl 2-butanol. The compound name is 3,3-dimethyl 2-butanol. It's actually a secondary alcohol. It's actually a secondary alcohol. Okay, so there is acid, in presence of acid. So the O, two lone pairs are there, two lone pairs, one lone pair donates to the H3O plus system. As a result of that, there will be a protonated alcohol. It forms a protonated alcohol. And you know what happens is that, protonated alcohol undergo dehydration. It gives off electron to form this carbocation. It's actually a secondary carbocation. You know that secondary carbocation is stable, I agree, but tertiary carbocations are more stable than secondary carbocations. So what happens is that this CH3 group migrates to actually this carbon atom. When the CH3 migrates to this carbon atom, there's a new bond between this carbon atom and the CH3. The new bond is formed here, but this carbon loses the bond and this carbon atom becomes positive charge. That is, this is actually a tertiary carbocation. And you know that tertiary carbocations are more stable. Okay, this is a more stable carbocation. In the third step, what happens is that this is a carbocation. The third step, what happens is that there's again water. There are two options here. We can take proton from this carbon atom. This is the beta carbon atom. This is also beta carbon atom. Or we can call that to be, okay, this is this carbocation containing carbon atom. This is the alpha carbon atom. This is the beta carbon atom. And again, this is also a beta carbon atom. They two are equivalent. So if the proton is removed from this beta carbon atom, it leads to deprotonation here. And you can see the bond shift towards here. And you can see that it leads to this alkene. And if this beta hydrogen atom is taken off by alcohol, by the water, what happens is that there is a bond between this carbon atom and this carbon atom here, and it forms this alkene. Two alkenes are here, possible here. And you can see that this alkene is more stable because it is more substituted. By Say-Safe rule, it is more stable. We get a more substituted alkene. The reason behind the stability of alkenes, it is nothing but hyperconjugation. This alkene is more stable. Okay, so you can see that here the elimination is, this step is actually regioselective. There are two options. This is the major product and this is the minor product. So the removal of proton is regioselective here and leads to such that it leads to this formation of more substituted alkene as a product. So remember that during the process, there is a carbocation is formed. So if there's a carbocation, if it's a complex structure, carbocations may rearrange. It's due to this called 1-to-methanol shift. CH3 shifted towards this CH plus. This is called 1-to-methanol shift. Sometimes it is called as 1-to-methyl shift. Better word is actually methanol shift, 1-to-methanol shift, and leads to formation of more stable tertiary carbocation. So it's very clear that carbocations can show rearrangements. Carbocations can show rearrangements. So this rearrangement of carbocation is typically called as the Wagner-Merwin rearrangement. This is typically called as the Wagner-Merwin rearrangement. It is a mechanism of the dehydration of 3,3-dimethyl 2-butanol. Where unexpected product is formed. This is the unexpected product. We never expect the formation of this product here. Okay, it's actually due to this process. So another method of preparation of this is actually carbocation is actually from benzene diazonium salts. Third method is from diazonium salts. So diazonium salt is CH3N2. This is actually methyl diazonium salt. This compound can undergo elimination of nitrogen. It shifted towards this place. And this carbon loses electron and it forms what? CH3 plus. So it's the third method of synthesis of third method synthesis of another method of synthesis of carbocations. And the fourth method, another method we can make from CH3Cl, alkyl halides. Okay, if you react with aluminum chloride, AlCl3, it's a Lewis base. Sorry, Lewis acid. So it will take the minus charge, minus U of electron to chlorine, and now it forms AlCl4 minus. And what's remaining? We will be getting CH3 plus. So Lewis acids can also influence the formation of carbocations. These are different methods of preparation of carbocations. So we have seen different methods. We have seen preparation from alkenes. We have seen preparation from alcohols. It's not simple, but it's a bit complex. We have seen preparation from amines. We have seen preparation from diazonium salts. Now we have seen the preparation from alkyl halides by using a Lewis acid. Our next topic of discussion is non-classical carbocations. Normally, classical carbocations are having carbon atom in a trigonal system. But here we can see that in this molecule, I think you might have studied that in the last semester in neighboring group participation. You can see that here, this is the system, the non-organelle system. And you can see that here, this is a plus charge in this carbon atom. This sigma bond, adjacent sigma bond, what happens is that adjacent sigma bond adds to this plus charge. As a result of that, what happens is that a new bond is formed between this carbon atom and this carbon atom. A new bond is actually formed between this carbon atom and this carbon atom. And this bond breaks. So this bond breaks and a new bond is formed. Consequently, this carbon atom gets positive charge. This carbon atom will get positive charge. Okay, so if you look into the resonance structure of these two compounds, you can see that this bond is no bond here. But in this structure, there is a single bond. The actual structure is between that of a single bond and double bond. That is called a partial single bond structure. So there will be actually a partial single bond between this carbon atom and this carbon atom. Okay, and what about here? Here also there is, in fact, there will be a single bond here, but here there are no bonds. So actual structure is in between that of single bond and no bond. Again, there will be a partial, or we can call it a partial single bond here. Rest everything is okay, same, no problem, no change. So the plus charge is delocalized over all the system. So you can see it is actually three center, one center, second center, third center. The three center bond. But actually here we have got only two electrons only. These two electrons are only going to her and only two electrons are only involved in this bond. So it's actually a three center, two electron bond. So here we can see that here there is delocalization of sigma electrons also taking place. So here we can see that delocalized sigma electrons also taking place, and the carbocation such form is actually what is called a non-classical carbocation. In these examples, you can see that there will be delocalized sigma and pi together. Okay. So we can say that during the formation of non-classical carbocation, there should be compulsorily delocalization of sigma electron. It can be combined with pi also, no issues. It's actually called a 3-center 2-electron interaction or 3-center 2-electron bond. We can see that we can consider this bond as an intermediate between the structure 1 and 2. So 1 is actually classical carbocation and 2 is again a classical carbocation. Okay, and this is actually the resonance structure 3 is actually between that of a primary and this classical cation, this classical cation. And you know, it's an intermediate energy will be high. So it's very clear that the energy of 3-center 2-electron non-classical carbocation is high, that means less stable. Okay, another example of carbocation is this system. You might have studied this also in neighbor group participation. It is called phenonium system. Consider here it is CH2 plus. There's a double bond here. I forgot to put that. You know what happens is that this bond shifts here. When this bond shifts here, a new carbon-carbon bond is formed here. This is formed over here. But you know, this carbon atom gets a positive charge. And the positive charge is delocalized to the system and also to the system. Okay. And this is actually what is called a non-classical carbocation. Here, there's delocalization sigma bond. This pi is becoming sigma here. And the carbocation is formed. So it's another example of non-classical carbocation. And the classical example of non-classical carbocation is CH5 plus. It actually considers classical example of non-classical carbocation. Okay, this compound is actually, we call that to be methonium ion. We can call that to be methonium ion. So it's actually formed as a result of the reaction between CH3 plus and H2. They can form CH5 plus. The structure of the compound is very typical. Carbon atom, there are 5 hydrogen atoms. This is a normal one. There's hydrogen here. And there's a positive charge. And hydrogen here, and hydrogen here, and hydrogen here. You can see that this is actually a 2-center 2-electron bond, normal 2-center 2-electron bond. But this bond, you can see this bond, 3 centers are here. 1, 2, 3. 3 centers are here. So this bond is actually a 3-center 2-electron bond. It's a 3-center 2-electron bond. It's a typical non-classical carbocation. The 3-center 2-electron bond. Okay, this is another example of non-classical carbocation. And the shape is trigonal bipyramidal. The shape is, in fact, trigonal bipyramidal. Trigonal bipyramidal is the shape of the system. Okay, if you want to know about this system, you can refer to the paper by Ola. He got Nobel Prize in chemistry. Okay, the reference is Journal of American Chemical Society. This is a journal. You can, the paper support 1969. You may refer to volume number 91, page number 3261. You can get a very thorough view of this non-classical carbocation, especially methanium ion. And in fact, he prepared non-classical carbocations by using superacids. His classical contribution. Actually, it is a very interesting area of study. So that's all about non-classical carbocations. So today we have discussed the stability of carbocations, structure of carbocations. We have seen the preparation of carbocations, and last we have seen non-classical carbocations. In the next lecture, we'll be looking into the different rearrangements where carbocations are involved with. So typically, just remember that carbocations can show rearrangement. That is called Wagner-Merwin rearrangement. Many classical reactions, the pinnacle-pinaclone reaction, reactions are actually, they show, they involve this rearrangement. So thank you very much.